Section 1.3 is all about the properties of functions. So let's take a look at these series of numbers. Can you find a pattern? Well, yeah, so this we're adding by 1 every time. This also looks like the natural numbers, right? Here, we're adding by 4 every time. Let's take a look at these ones. Okay, here I've got 1, 13, and 25. Well, it looks like each time I'm adding 12. But this same trick doesn't work for this one right here. I've got 1, 4, 9, 16, 25, and 36. What types of numbers are those? Well, these are perfect squares. So I've got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, so on and so forth. These are examples of sequences. A sequence is a function that computes an ordered list. Its domain is the natural numbers, and sequences can be finite or they can be infinite. So that means they're countable or they can be uncountable. So friendly reminder that the natural numbers are 1, 2, 3, 4, 5, right? Those are what we call our counting numbers. And a finite sequence has a set of natural numbers as its domain. Remember, domain are our x values, our independent variable, our input, and they have the form 1, 2, 3, 4, 5, all the way on until n. An infinite sequence also has the set of natural numbers as its domain, but an infinite sequence has no final numbers. We will denote n to denote a natural number and capital N with an extra slash to denote the natural numbers. So there are 3 ways to describe an output of a function defined over the natural numbers. So we can do it using a formula, using a recursive formula, or an implied rule. So let's take a look at each of those. So if I use a formula, that means that for each new value of a sequence, it doesn't depend on the sequence entry before it. So let's say I had this, the function from the natural numbers to the natural numbers, right? So my domain is the same as my target, and I define this so that S of I is I squared, where I is an index, right, for our natural numbers. So let's write the first 5 terms of this sequence. S1 would be 1 squared, which is 1. S of 2 would be 2 squared, which is 4. S of 3 would be 3 squared, which is 9. S of 4 would be 4 squared, which is 16. And S of 5 would be 5 squared, which is 25. Okay? So we're using I as an index to tell us which natural number we're on. So now let's look at the function k. It also goes from the natural numbers to the natural numbers, but k is defined by 2i plus 1. So let's write the first 5 terms of this sequence. K of 1 equals 2 times 1 plus 1, which would give us 3. K of 2 gives us 2 times 2 plus 1, which is 5. K of 3 gives us 2 times 3 plus 1, which is 7. K of 4 gives us 2 times 4 plus 1, which is 9. And K of 5 gives us 2 times 5 plus 1, which is 11. So the first 5 terms of this sequence are 3, 5, 7, 9, 11, and we get to do a dot, 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 because we know it keeps on going. The other way we can define a function is using a sequence for a function is using a recursive definition. So in recursive definitions, each term after the first term depends on the first term before it. So each new term depends on the term before it or on multiple terms before it. So let's take a look. Let's say a sub 1 equals 4. Then a sub 2, a of 2 would equal 2 times a to the 2 minus 1 plus 1. So a of 2 is 2 times a of 1 plus 1. Well, that gives us 2 times 4, which is 9. So a2 is 9. Now, if I want to find a3 is 2 times a of 2 plus 1. So a of 3 is 2 times 9 plus 1, which is 19. Next, a of 4, I'm running out of room, a of 4 equals 2 times a of 3 plus 1, which is 2 times 19 plus 1, which is 38 plus 1, which is 39. And a of 5 is 2 times a of 4, which is 39, right? Plus 1, which gives us 2 times 39 is 78, plus 1 is 79. So my numbers, the first 5 terms of the sequence are 4, 9, 19, 39, 79, and it keeps going on. The Fibonacci sequence is the most well-known sequence, and it uses a recursive formula. Okay, so for the Fibonacci sequence, the Fibonacci function f sub n from n to n is defined as our first term is 1, our second term is 1, and then our third term, f of n plus 1, is going to be f of n plus f of n plus 1. So if I wanted to find f of 2, that would be f of 1 plus 1, which would be f of 1 plus f of 1 minus 1, which is f of 1 plus f of 0. So I'd have 1 plus 1, which is 2. Then f of 3, which is f of 2 plus 1, would be f of 2 plus f of 1. So I would have 2 plus 1, which would give me 3. F of 4, which it would be f of 3 plus f of 2, which is 3 plus 2, which is 5. F of 5 would be f of 4 plus f of 3, which is 5 plus 3, which is 8. And it keeps going on and on like this. So we've got 1, 1, 2, 3, 5, 8. And see that each new term is the sum of the two before it. So if I wanted to say what the next term was, I'm going to get 5 plus 8, which is 13. Then 8 plus 13, which is 21. Then 13 and 21, which is 34. And it keeps going on like this. The last way we can describe a sequence is using an implied rule. And it uses ... to let the reader recognize the pattern. So I've got 2, 3, 5, 7, 11. Well, I could say, oh, it's all the odd numbers, but I've got 2, so that means this is all prime numbers. So my next number would be 13, 17, 19, 23, and so on. Let's look at the function s where it's 2, 4, 6, 8. Well, this would be all even numbers. So it requires the reader to recognize the pattern.